We're going to move on now into this idea of what's called electromagnetism. Obviously, there might be a couple different things going on here. Just looking at the word, we've got electro and we've got magnetism. So we're going to start combining two ideas at the same time. And people figured this out about 100 years ago, I guess it was, the relationship between electricity and magnetism. And things you remember from when you, long time ago in a land far, far away, you had this idea of what's called magnetism. There was this force of attraction or repulsion. You know, people noticed it with metals. People noticed it actually with rocks, with hematite. If you've ever had a piece of hematite, it's a metallic rock. Well, magnets have a north pole and a south pole. It's basically, just like there were positives and negatives before, now we've got a north and we've got a south. The difference between magnetism and electricity, however, is a north pole can't be separated from a south pole. Okay? You can separate a negative charge from a positive charge. But with magnetism, you can't separate north and south. If you have one big magnet with a north and a south, and you split that, okay, you get two magnets and both have a north pole and a south pole. Just like opposite charges attract, opposite poles attract. Like poles repel. Okay? Not every material can be magnetic. The most common you'll find are iron and nickel and in cobalt. Okay? Iron and nickel are very, very common. It's one of the ways, if you ever see those things on TV where they're trying to see if somebody's ring or a piece of jewelry is fake or real, well, the first thing they'll do is they'll pick out a magnet and see if it's attracted. If it is, the base material is probably iron or nickel and not gold or silver or something that's really important. Okay? The Earth has a core of iron and nickel, okay, inside, and we're spinning, so we actually have a magnetic field around the good planet Earth, okay? And this actually protects us from a lot of stuff a lot of the charged particles that are going on in the solar system, because this acts as a defense mechanism. When we're talking about an individual nail or an individual piece of metal or an individual magnet, you get what's called domains. And domains are areas in substances where the atoms are magnetically aligned. Why are they magnetically aligned? Well, magnetism, anything magnetic, is caused by an electron moving. When you have an electron moving, you get a magnetic field. Now, what happens in some of these elements, you're either moving around a nucleus or you're spinning. Okay? So how do you get something that is highly magnetic? That means these electrons are moving the same direction, or they're spinning the same direction. Remember back in chemistry when you learned about electron spin and why that was important? That's just one of these things here. It gives it a magnetic property if they're all spinning the same direction. You get a magnetic field around a magnet, okay? Again, just like electricity, you get these magnetic field lines. Well, these magnetic field lines go from north to south, okay? From north to south. If you look at these compasses, if you put a compass around a magnet, okay, it's not going to go to the Earth's magnetic poles. It's going to go into the field around that magnet, okay? So the south, you've got a south-seeking pole and a north-seeking pole on those magnets, okay? But here, you'll see, right, we're pointing towards that. Or the compass will always end up aligning itself along those magnetic field lines. And when you draw the lines, the closer together they are, the stronger they are. The farther apart, right, the weaker. Same idea still remains. with the good planet Earth, right? Again, you've got this iron nickel core in here, and it's actually, since the Earth is spinning, what are you getting? You're getting a magnetic field. Okay? You're getting a magnetic field around the Earth simply because we have a metallic core, and that core is actually spinning. Once those electrons start spinning, you get magnetism. So can you induce magnetism? Yeah, probably you can. Could you induce a charge? Remember when we were dealing with electrostatics and we induced a charge, right? The same types of things can happen, okay? If we have a magnet, and that's the north end of the pole, and that's the south end of the pole, you know, if this is an iron nail, right? Things that you know in these types of metals, the electrons like to move freely, okay? That means the electrons on one end can be oriented one way and the electrons on the other be oriented the another way, okay? So you have to think about what's going to happen between this magnet and the nail, okay? Remember, opposite poles attract, like charges repel. And we're going to talk about this in class a little bit, so we can figure out how do we induce, can you make something a magnet? You know, and that's one of the ways that they originally made compasses. Okay, you took that needle, which was, at the time, it was really just a needle from a needle and thread. You brought a magnet to it, oriented it a certain way, and then carefully dropped that pin or whatever it was, or that needle, onto a little bubble of water, and it was free to move. Well, it went a certain way. It moved a certain way. Okay? Let's see what else we got. Those are the basics so far. We'll get into this guy in just a little bit, but we're going to stop right here. You know, things that you got to remember. What's good to remember? The Earth has a good magnetic field. Magnetic field lines, close together they're strong, far apart they're weak. The magnetic field lines go from north to south, okay? And why? Well, we've got these domains. The domains are important. Those are those areas where the electrons are aligned. We're spinning the same direction, or we're moving the same direction. Okay? Magnetic field of the Earth is actually a pretty cool idea. And then we'll talk about inducing magnetism. Okay, thank you very much. We'll be up for part 2 in a little bit.